Hello everybody. These are the notes for LT5 velocity time graphs. The ultimate goal is to describe and analyze the motion of an object when given a velocity time graph. So as opposed to LT3, where we were looking at just position, now we are looking more at a how fast and in what direction type of graph. So if you were in class, I gave you one of these and you glued it into your notebook. If you missed class for whatever reason, I have some extras. You'll have to get them from me. But hopefully you can see this one well enough that we can at least talk about it as we do the notes. So, first thing we need to do is review what the slope means on, I'm just going to say a DT graph or distance time graph, because that is not what it means anymore. All right, so slope on a distance time graph versus slope on a velocity time graph. Okay, so you think back, and we've been doing things with this type of graph for quite a few days now. So I wrote out the coordinates in case you do struggle to see this line. Okay, but we have 1 second here, 2 seconds, 3 seconds, 4 seconds. We start at 0, 0. We go up to 235 in 2 seconds, and then in 4 seconds we are at the 10 meter mark. So hopefully, if we call this line A and this line B, we now know that this is a positive slope, this is a negative slope, and if we could see that runner, we know anytime there's a positive slope, it's going to the right, and if we have a negative slope, it's turned around and went the other way, they're going to the left. So if we look, and we were on to figure out the slope for A, well, it's the change in Y over the change in X, but that ultimately is going to be distance divided by time. So at this point, we need to know that that gives you the velocity of the runner or the object, whatever it is. So the slope on a distance time graph tells us the velocity. The slope on a velocity time graph ends up telling us the acceleration. And I'll explain that more here in a second. For right now, just write it down, and then hopefully it'll make sense here in a minute. All right, so let's figure out for line A. Line A on a distance time graph, let's actually calculate the slope. We know it's the change in Y divided by the change in X. So our up and down motion, it's the end minus the beginning. So at the end of this time interval, we are at 35 meters, and we started at 0. And we've taken 2 seconds. That's a 2-second interval from 0 to 2. Okay, so that gives us a slope of a positive 17.5 meters per second. The positive tells us the runner is moving to the right, and the speed combined with the direction now is our velocity is 17.5 meters per second. So if you look now on this velocity time graph, you can see that this horizontal line here, that is representing the A portion of this runner's trip. Okay, because that line is drawn at 17.5 meters per second. Because this is velocity and this is time. You know, that's small to see. Okay, velocity and time. And so this is drawn horizontally at 17.5 meters per second. All right, so there's the A portion. If we wanted to figure out slope for B, still change in Y over change in X. But this time, remember, it's where you end compared to where you start. So we ended at 10. We started at 35, so 10 minus 35. From here to here is still 2 seconds. Okay, so 4 minus 2, if you couldn't do that in your head, 2 seconds. And so we have a negative 25 divided by 2, which is a negative 12.5 meters per second. Okay, negative 12.5. And so if you take it over here now and you look at its matching velocity time graph, well, that makes sense now. That's line B, and it's negative 12.5 meters per second. So if you wonder like how these computer programs, like you just click the tab on the gizmo and it gives you this, but that's where it's coming from. That computer is just calculating the slope and then transferring it onto a velocity time graph. So this little thing right here, where it drops down, that is where the runner turns around at. And this runner is clearly superhuman anyways, because, I mean, nobody's going to run 12 and 12.5 meters per second or 17.5 meters per second. And similarly, like this person doesn't even have to like slow down to turn around. That's one heck of a spin move right there, okay, to actually just pivot and adjust to 12.5. All right, so real quick, slope on a position time graph is the velocity. That gets transferred onto a velocity time graph. So now, why are these horizontal? Okay, because we knew on a horizontal line on a distance time graph, hopefully we would remember that that person, that object, whatever it is at rest. Because if, I don't want to get this all ugly, but if I just had a flat line at 10 meters, that means that person or that dog or that whatever is not moving. Okay, this person's moving. They're moving 17.5 meters per second. They're moving 12.5 meters per second to the left. So on a horizontal line on a velocity time graph is different. That means they are not accelerating. Okay, so acceleration would equal 0. Same speed, straight line, not accelerating. Technically accelerating here because they're turning, okay, so that's why it's not horizontal anymore. And then horizontal line going a constant 12.5 meters per second to the left. Okay, so hopefully you can now see how we get these velocity time graphs based on position. One thing a velocity time graph does not do is tell you where something is located. So from this we can calculate the velocity. We can see it's no acceleration, and we can see exactly where they're at. We can see position. But if I just gave you this and said, hey, where's that runner at? Who knows? Okay, there's no way of knowing where that runner is at. So they're both useful in their own ways. And I think that is it. So good luck.